In section 1.1, we talked about sets and we talked about subsets. So a subset is just a relationship between two sets where all of the elements of one set are also elements in the other set. But not all sets are necessarily going to have that relationship. Most of them won't. And so it's often useful to talk about other sorts of relationships that sets can have, right? So we might want to know whether two sets that aren't necessarily subsets of each other have elements in common or not. And we often can use a Venn diagram to help represent the relationships between these sets. So as an example, let's say A and B are sets of natural numbers where A is the set containing 1, 2, 3, 4, 5, and B is the set containing 3, 5, 6, and 7. So a Venn diagram just has sort of two possibly intersecting circles, and we place the elements of those sets into those circles based on which set they're in, right? A, B, or this overlapping part would represent both. So 1 is in the set A but not B, so we put 1 over here. 2 is also just an A. 3 is an element that's in both sets. So it's in A but it's also in B, so it's useful to put it here in this middle section here, right? Because now it's an element of both sets. 4 is just an element of A. 5 is an element of both sets, A and B. That's it for A. We've covered all 5 elements of A. Now B, we have 3 and 5 in there already, and then 6 and 7, which are in B but not in A. So I'll put those over here, 6 and 7. All right, now just one thing that I want to point out quickly. I put little dots next to them to represent that we're actually talking about specific elements of these sets. Sometimes you'll see people draw a Venn diagram and use the Venn diagram to represent cardinality of particular areas, right? So if we had a cardinality Venn diagram to represent this particular relationship between A and B, it would look like, here's A, here's B. We would write down, well, how many elements are just in A but not in B? There's 1, 2, 3 of them. How many elements are in both of these sets? Well, just 3 and 5, so there's 2 of them. And how many elements are in B but not A? There's 2 of them. Right, so just to clarify, just to make sure that we're keeping things straight, I'm going to put little dots next to the elements here to represent actual elements. If I don't have dots, then that means I'm talking about cardinality. It's just something that we want to be careful about. The other thing that you might have noticed is that in this actual element Venn diagram, I put a box around everything. That's because anytime you're talking about two particular sets, they have to exist in some sort of universe, right? It could be that the universe just happens to be the numbers from 1 through 7, but I had said at the beginning that A and B are sets of natural numbers. So the natural universe here that we would be talking about is just the universe of natural numbers. And there's a lot of other natural numbers that aren't in A or in B. They live somewhere, so I just put a box out here, and all of those natural numbers that aren't in either set are going to sort of live out here in the box, right? So 8's out here, 9's out here, 10's out here. I certainly don't want to do this forever, so I'm just going to put a ... to indicate that, you know, there's other elements here as well, right? Oftentimes we call this sort of larger box here a universal set. So in this case, the universal set is going to be the set of natural numbers, but it'll maybe change depending on the context. Now notice that we had found that there were 2 elements that were laying in both sets, right? 3 and 5 are in both sets here. And so in general, if we want to talk about the set of numbers that happen to fall into 2 or maybe more different sets, we call that the intersection of 2 sets. So we say the intersection of A and B, which we denote A intersect B, so this is a sort of an upside down U symbol. That's the set of elements that are in both A and in B. So in our particular example up here, A intersect B would be the set containing the things that are in both A and B. That would be the elements 3 and 5. So in a general Venn diagram, when we talk about the intersection of A and B, we're talking about all the things that lie here in the middle. So you might see a Venn diagram like this to represent the stuff that's in A and in B, right? The stuff in the intersection of A and B. But we could also talk about, you know, what do we get if we try to just join these 2 sets together, right? The union of A and B is going to be the set of all elements that are in either A or B, but also could be both. In math, an or isn't necessarily going to be an exclusive or. It's not saying A or B, but not both. It's saying it could be both as well. It's an inclusive OR. And so for us, A union B is going to be anything that's in either one of these circles. So 1, 2, 4, 3, 5, 6, and 7. Or maybe it makes more sense to just write them out in order. 1, 2, 3, 4, 5, 6, 7. Remember, order doesn't matter in a set, so you can write those elements in whatever order that you want, as long as you actually end up getting everything that's in A along with everything that's in B. You might be tempted to just sort of write out all the elements of A, right? Copy them from here, 1, 2, 3, 4, 5, and then copy out all the elements of B, 3, 5, 6, 7. But this is a little redundant, right? It's saying that 3 is an element of the set, and then it's saying that again later. It's saying 5 is an element of the set, and 5 is an element later. So it doesn't make sense to say it twice. So just list 3 and 5 only one time when you're talking about the union of these sets. And just like before, we can give a general Venn diagram picture of the union of A and B. Here's A, here's B. The union is just everything, right? We're gonna shade in everything in A along with everything in B. All right, so let's look at a couple more examples. So it looks like these sets C, D, and E are living in a universal set of, let's say, the lowercase letters of the alphabet. So C has X, Y, Z, W, D has T, U, V, W, E has R, S, U, W, Z. So we can talk about these sorts of different relationships, intersections, and unions. Remember, if you see the upside down U, that means intersection, right? It sort of looks like an N. Well, that doesn't really help. I think about this sort of intersection symbol up here. The way that I remember it is you can sort of put a line through the middle and turn it into an A. The intersection is the stuff that's in A and in B. The U is for union. That's joining everything together. All right, so this is C intersect D. This is the set of all things that are in both sets. So what elements are both in C and in D? Well, it's not going to be X, because X isn't here. It's not going to be Y, because Y is not here. It's not going to be Z. Z's not here. W. W is the only one. Right? Similarly, T, U, and V are not in C, so they're not going to be in the intersection. What about D intersect E? The stuff that's in both D and in E. We've got W, V, U, T over here. It looks like W and U are in both of those sets. T and V are not in the second set, so they won't be in the intersection. So the intersection here is going to be U and W. And the union, C union E, is a collection of everything in C along with everything in E. So I'm just going to list out all my elements of C, X, Y, Z, W. Then I'm going to list out all my elements of E, R, S, U, W. Oh, careful, we don't want to list W twice because we've already listed it, and I don't want to list Z twice, I've already listed it. So I'm just going to end my set here. So that's what I get for the union. But we can extend this idea of intersections and unions to more than two sets. So when you see something like this, C intersect D intersect E, it just means we want the set of all elements that are in the set C and in the set D and in the set E. We want the elements that are in all three sets. So what elements occur in all three of these sets? Well, at best you're going to get just a W, right? Because C and D has an intersection of W. So you can't get anything more than that. As long as W is actually an element of E, then that's going to be in the intersection of all three. And it is, right? W appears in all three sets. So this three-way intersection contains W. The union, C, union D, union E, is going to be everything, right? All of these sets put together. So X, Y, Z, W, T, U, V, don't list W again, R, S, already listed U, already listed W, already listed Z. Okay, so this is it. That's my union of all three sets. And we can also have a Venn diagram to represent the relationship between all three sets. All right, the thing is we have to make sure that we have three circles here. And we have to make sure that we very carefully place where these lie in the intersections. So, let's see. X is an element of just C, so we'll put X out here. Y is an element of just C. Z, we said, was an element of C and of D, but not, C and E, but not D. All right, so to be in C and in E but not in D means I have to put it in this spot right here, right? It can't go in the three-way intersection because it's not actually an element of D. But W we said was in all three of these sets, so we'll put W here. All right, those are all my elements of C. Now T is just an element of D, so we'll put T here. U is an element of both D and E, so we'll put that here because it's not also in C. V's already there. Oh no, V's not there yet. So V is just an element of D. W we said was already in the three-way intersection. And finally, what are we missing? We've got R, that's just an E. We've got S, that's just an E. U is already there, W is already there, Z is already there. So you'll notice that every single one of these elements, X, Y, Z, T, U, V, R, S, appear exactly once in the Venn diagram. You don't want anything to appear in that Venn diagram more than once.